Anyway, as I was saying, so TECS has turned 10 this year, but the other impetus for providing a tuning update is that since the last conference, we've updated the TECS control loops. And what that's done is it's done two things. It's improved the control over the flare maneuver so that we no longer run with a open loop sort of sync rate demand when we reach the flare. And we've also rejigged the control loops to make it less susceptible to integrator wind up and overshooting its height or undershooting its height when reaching altitude. And I'll talk about the EKF status because if I don't talk about it, no one else will talk about it. Also, we've made some changes which will be of interest to those of you that fly copters. Okay, so very quickly, nav EKF, it's a fairly stable code base at this point in time, but we did have 5 new feature pull requests, but the majority were bug fixes and some code improvements. And I can actually just close this down, I think, without upsetting it. All right, I'll move that down to the bottom. Okay. The first item, and this is an important one that previously we were using, if you requested by the parameters to use GPS as the primary altitude source, it would use GPS as the primary altitude source if it had a 3D lock, regardless of the recorded accuracy for the vertical position. So that's now, you can now specify the required accuracy before we use that GPS height. Do we have an audio coming through? Okay, yep. The other item which is probably of interest to and this would be more of interest to the copter community, is we've already merged a pull request which enables the use of drag fusion, which I covered on I think the 2021 IG Pilot conference, and enables the copter to estimate the wind drift using the measured drag in the X and Y direction. And then we can use that to perform a very basic dead reckoning function if you lose GPS and extend the amount of dead reckoning time. Now, an improvement to that's been made that locks the wind estimate in when you start to dead reckon. And Randy flew that out at CMAX just a couple of days ago, and we were holding. He had thumbs up. We were holding position in the wind with GPS turned off. Obviously, the accuracy then degrades once you start moving because the way that the copter measures drag, we don't have a drag model that's valid for all angles of wind arrival. And there's a prototype piece of code which, thanks to Pete Hall for making wind vane library available to where we need it in the EKF, and I've plumbed it through to the EKF. And we're going to do some testing with using ultrasonic wind sensors on copters to give you some much more accurate wind relative dead reckoning. And the impetus came from looking at the ultrasonic sensor on the mast of the sailboat. In fact, we wanted to distract Pete so that we could saw the top bit of his mast off and then hot glue it on top of the copter. But we couldn't distract him. So that's going to be going into the code base in the next 12 months if it's successful, and we'll be looking for flight test volunteers for that. Okay. So if we're talking about that's the new functionality. There was a performance improvement. We now do better with planes with airspeed fault detection. So now if the airspeed fails, before we declare the airspeed as good again, we check its consistency with the wind estimates in the EKF and the airspeed measurement, and we don't start using the airspeed sensor until it's been providing reasonable estimates for a period of time. And a shout out to Alex, who's one of the partners for the race, for doing the flight testing for that. And I won't go through the boring minutiae of bug fixes and code improvements. Okay, so TECS, Total Energy Control System. What does that mean? You can describe it in one sentence. It means you're controlling speed and height using some combination of throttle or thrust control and pitch angle on the aircraft. And why do we talk about total energy? Well, an aircraft has two forms of energy. One is the energy stored in the height. It's the energy you get if you take a brick up to the top of your house. It's got energy stored in it. If you drop it off the top of your house, when it gets to the bottom, that energy is being converted to kinetic energy, which is the speed in the brick. So potential energy varies with height. Kinetic energy varies with speed squared. And total energy is the combination. It's the sum of potential and kinetic energy. And when an aircraft dives to pick up speed, what it's doing is it's converting potential energy stored in it, due to its height, and it's converting that to potential energy. When it climbs back up again and it slows down, it's converting energy back the other way. Now, we're always losing energy. Even in the most efficient glider, energy is being lost all the time, and that's what the throttle's for. So we use the throttle to replace the energy that's lost, or to add total energy if we need to climb, or to reduce energy if we need to descend. And then we use the pitch angle to control the exchange between potential and kinetic energy. And intuitively, you think about it, it's a simple concept. There's some mathematics involved, and those mathematics do rely on calibrating the throttle for the rate of change of height of the aircraft, and that's something that I'm going to talk about. I'm not going to talk about block diagrams. I've put them in because there are some GNC trained people in this room. If I don't put a block diagram in the presentation, they're going to ask for one. So I've got a block diagram here for the pitch demand controller, showing how the energy quantities are derived and how control. Nerd out on that, not many I suspect. And similarly for the throttle loop, okay, which controls the total energy. And this third diagram, which I am going to draw people's attention to. This is the important one. This is really where, in some respects, if you're flying a TECS and you lose your airspeed sensor, or you're flying without an airspeed sensor, we revert back to a mapping that says, it makes the assumption that you're flying at your cruise speed, and it sets the throttle based on the pitch angle of the aircraft. And as you can immediately intuit, that getting the right mapping, having that throttle maximum being sufficient to maintain a safe airspeed when you're demanding your maximum pitch angle, that's important. And similarly, to avoid overspeeding on cruise or overspeeding on descent. So a lot of the TECS tuning is really about matching the throttle to the climb rate and to the pitch angle, and getting that right. And when you get that right, there's usually very little else that needs to be tuned. Okay, but before you want to tune TECS, there's some things that need to be done first. If you get this out of order, then you end up having to go back, then you have to redo these items, and then you have to go back and tune your TECS, and it's time consuming. So the first thing, and I'm not going to talk about pitch controller tuning much at all, because we've got a wiki for it now. We have an auto tune process for plane users, but start off with tuning the pitch controller, and don't have to go super aggressive on the gains, but it does need to accurately, to a reasonable degree of accuracy, to within about plus or minus a degree in sort of light wind conditions, to be able to follow the demanded pitch angle. Then we need to set the pitch angle datum. What's the pitch angle datum? That's ensuring that if you were to fly in fly-by-wire with a zero pitch demand to the controller, that the aircraft would fly and not lose height or gain height. And then there are two methods of achieving that. Then we need to set pitch angle limits to make sure you can't pull up, too steep a climb or too steep a descent. And then obviously we need to set appropriate airspeed limits, and that means understanding your stall speed. Okay. Then once those items have been performed, then we go into TECS. And the most important item is vertical speed to throttle mapping. And we have 4 flight conditions. We have cruise, which is level flight, your maximum climb. There's gliding, where you've got power off and it's just descending at your mission speed. And then there's what you define as your maximum descent. How fast can I descend, or do I want to descend, or can I descend without overspeeding the aircraft? Then we get on to some of these other items that are optional. Do you want to finesse with the gain tuning? and there are some, we'll talk about that. But the primary focus is going to be on the speed throttle mapping, and then there's some items that you can use to improve the landing approach in the flare manoeuvre. Okay, pitch controller tuning. Where this is a little bit different to just one, once you start incorporating the pitch controller and demanding it using TECS, there's one behaviour that a number of aircraft have, and for example, a Bixler. For those of you that are familiar with fixed wing RC, some of these foam aircraft that people use have high mounted motors. And the problem with having a motor that's mounted offset from the centre of gravity of the aircraft or the centre of drag is that when you apply throttle, the aircraft wants to pitch up or pitch down. And if there's one thing TECS doesn't like, because it's trying to demand a pitch angle to do one thing, which is control the exchange, the flight path angle, control the exchange between energy, and it's using throttle just to add energy. If it's one thing TECS doesn't like, it adds throttle, and that causes the pitch angle to change. Right? So that's why getting the pitch controller tuning correct is important. And now, if you've bought the aircraft and the thrust line is the thrust line, you can't do much about it. That's the characteristics. What you can do when you tune the pitch loop is ensure that you can use a little bit more integrator gain. I'm not going to go into this in detail, but the best thing to do there is to turn up your integrator gain, and then you can turn down the time constant. Also increase the time constant, which turns down the angle gain. So if you turn up pitch rate I and turn up pitch to servo T const, so you have a faster integrator, and the integrator is what reacts and responds to the change in the aircraft trim. So that's the thing to remember about. Integrator is like an auto trim. The bigger the integrator gain, the faster it retrims the aircraft to allow for changes in thrust. We've got a pitch loop tuning documented, and there's also an auto tune option, and those, I've got hyperlinks there that will take you to the relevant pages. Okay, now pitch angle datum. There's two schools of thought about how to get RG pilot to fly straight and level without gaining or losing height in fly-by-wire A, which is where you've got zero pitch demand at the stick. That's also what TECS controls via. One, the first method is to put the aircraft at what you regard as its flying attitude, which is slightly nose up. It might be 4 degrees, 5 degrees nose up. And when you do your accelerometer level calibration, and that's what you do. The other method is to tune the aircraft so that it's at a zero angle, what we call zero deck angle, or zero angle for the fuselage, or whatever the convenient datum is to the aircraft. It might be the underside of the fuselage. It might be the wing saddle. It might be the quarter line of the wing, or the angle it sits on the undercarriage. And then you adjust trim pitch CD until it flies level without gaining or losing altitude when you're flying in FBWA. And people will argue for and against those two methods. You've done that. Now, we talk about pitch angle limits. That's a lot of words there, but it really means that you need to allow about 2 degrees margin, and this is rule of thumb, above the angle required to achieve your maximum TECS climb rate. So I've got a calculation there that enables you to go from the maximum TECS climb rate and the airspeed and calculate approximately what that parameter should be. Okay, you may have to adjust it, but for those of you that don't mind getting onto your calculator, saying, I've got my climb max, I've got my trim airspeed, I need to get a number for pitch max, that's a simple formula that can be used. And then you need to make sure that the overall limit, the limit that no controller can exceed, and that includes the pilot in FBWA, that's limb pitch max. That needs to be that can't be smaller than TECS pitch max, because TECS will take the smaller of those two parameters. Okay, so we set the maximum pitch angle limit, and then we set the minimum, and it's a similar concept. You need 2 degrees of margin. And you also need to make sure that the global minimum pitch angle limit is no more than the TECS value. In other words, it can't be above; it can be below. We set pitch angle limits, and by the way, if you've got questions because of what I'm doing here, probably appropriate just for people to stick up their hand and say, yes.
Where is the 2 degrees coming from? Like,
The 57.3.
so the 2 degrees, like why 2 degrees? Why
Because you have a little bit of turbulence. That's just due to turbulence, gust response of the aircraft. And there can be some fluctuations around that.
right, but why 2 degrees? Why not 3 or 4 or, you know, 1?
I said rule of thumb. 2, I found 2 to be adequate for most applications.
Is it an aircraft requirement or like it can be like it's generally
The problem you'll have if you go too high. Okay, so just for the recording, the question is being asked, why a 2-degree offset as a rule of thumb for the TECS pitch min and pitch max? Well, firstly, it's got to be sufficient to a little bit of margin for gusts. But if it's too much, remember we had a throttle mapping if we lose our airspeed sensor, and TECS defaults to demanding a throttle as a function of the demanded pitch angle. And if you've raised your pitch angle limit, then that essentially reduces the throttle it applies when you're climbing, and you end up with an underspeed. Yes.
So typo, the first paragraph you're saying lim pitch min. That formula is for TECS pitch min. Lim pitch min applies in flow ORA. TECS pitch min only applies in auto.
Yeah, but TECS, yes, that's true, but TECS takes won't allow TECS pitch min to be a more negative value than lim pitch min. Yes.
Yeah.
Okay. So you can't have one. So there, lim pitch min, it needs to be set. TECS pitch min.
In the top.
Oh, yes. Sorry.
That should have been TECS pitch min in that.
Yes, you're correct. Yeah, that should be TECS pitch min. I'll fix that up for the.
The slides. The last sentence of that first paragraph.
Yeah, TECS pitch min. Yeah. Okay.
No worries.
Thank you for that. Yeah.
Just don't want people setting it off by a factor of 100.
Yes, because 70 degrees versus degrees. Well. And by the way, not all of the parameter quantities that are in 70 degrees finish off with CD.
Yeah, I think even for IGFL 4.5 or 5.0, we should aim to get rid of all
70 degrees. Oh, here.
Yes. Switch.
Yeah, so the comment for the recording is that the proposal is that we eliminate 70 degrees for units in parameters for future major releases. At the back.
So that equation for TECS pitch min, it seems like that doesn't account for the angle of the path, the wing.
No.
On screen just now.
The answer is yes, it does, because we've set our pitch datum. So the question is that formula for TECS pitch min doesn't account for angle of attack of the wing, and the answer is it does if you've correctly set your pitch datum. So that a 0 TECS pitch demand is level flight. Yes.
Well, can I just ask, on the previous slide, sitting pitch datum, you said there are 2 schools of thought. Which one would you recommend?
Yeah, okay, so the question is, there are 2 schools of thought for setting pitch angle datum. Which would you recommend? Personally, because I'm trying to also do other things like do datums for camera systems or things like that on the aircraft, and trying to jig an aircraft to get a camera to align. I personally use trim pitch CD because I want a consistent mechanical datum, and I'd rather have that as the basis to get consistent results for the setting. But for other users where I just want to put my plane on an angle on the ground that looks like the angle it flies at, and then just go and hit the level for their accelerometer calibration, that suits their use case better. But if you're somebody that's fastidious about setting datums up on your aircraft, I would recommend the second method.
And just to back that up too, if you are running a quad plane, if you want to set that datum for your lift surfaces, which should be just and your angle of attack of your wing should be just a fraction positive versus those lift surfaces, but not too positive.
Yes.
And so then you go it further supports your risking it.
So the comment is that there's a use case for quad planes, and that's a valid point, because you certainly want with a quad plane You do not want a quad plane that has a 0 pitch datum with the rotor discs, with the rotors angled backwards. That's not for the 0 datum, but when it's in VTOL. So I would certainly recommend the second method for quad planes. I will fix that up. TECS pitch mean. I'll fix that up later. Okay. So we've done airspeed limits. Now the first point, very important. If you don't know the stall speed of the aircraft, you can try and find it from maybe somebody else that has logs for the aircraft. The best way to find it is to look at what the airspeed sensor measures just before, when you're flaring and the aircraft just starts to sort of stall onto the ground, and that really defines your stall speed. It's that final round out and flare. Typically, now this can be difficult for people that don't fly, are unable to fly a vehicle in a manual mode, and in that case, it's better to be conservative. So you're better off setting the FBW min to be too high than you are setting it to be too low. My preferred method for measuring stall speed is to either be in fly-by-wire and measure it from the logs based on the landing when you're just pulling back on the stick and you're trying to reduce the sink rate, and then I'll look at the airspeed sensor and what was I seeing as the aircraft just started to stall and lose lift, or you can fly it, or I can fly it in manual mode and just slowly reduce throttle, pull back on the stick, and there's watch until the nose comes down, and then look at the flight log. The maximum value, importantly, you need to respect the concept of battery state of charge and loss of battery voltage when you set the maximum airspeed. And the reason this is important is that if TECS is trying to achieve a maximum speed and it's unable to achieve the speed, it will start to lower the nose to try and achieve the speed, and that will cause it to fly below the demanded flight path. And you will end up with a scenario where the height loop is trying to pull the nose up to gain height. The speed loop, or the speed control, is trying to push the nose down to maintain speed, and you could be flying 15 metres below your demanded flight path, or 20 metres below, with the throttle at maximum. So yeah, think about battery state of charge and think about the voltage range for the battery when you set that. There needs to be enough headroom or margin on the throttle maximum to allow for that. And then finally, and the final item is something not to forget, that is the trim speed has to be somewhere between your minimum and maximum. I've seen trim speeds, I've seen the minimum speed raised on a platform and they forgot to adjust the trim speed. So it was flying around a minimum speed for the entire flight. Okay. Now, this is the biggie for TECS flight testing. So now we've gone through, we've tuned our pitch loop, we've set our pitch angle datum, we've set our pitch limits, we've decided what speeds we can fly at. Now we're going to start tuning the TECS, calibrating the TECS. Now the first one, the most important one is the cruise condition. And you could, that can be just obtained just by monitoring the throttle that the aircraft is using while it's flying level in an auto mode, because level flight, the tuning has much less of an impact. It'll automatically throttle up or down to achieve the demanded speed. Just check for the throttle that it's using, and then you just update the parameter accordingly. And that would be a very easy, in fact, if we're auto tuning TECS, that'd be the starting point, just to adjust the trim throttle. The second item is maximum climb. Now, I didn't want to talk about voltage compensation, not in detail, but if you're not compensating, if you're measuring battery voltage and you're not compensating for it, then the question is why not? Because what will happen is that as the battery reduces and reduces, you can end up with a situation where there isn't sufficient throttle to maintain your maximum airspeed. or the airspeed will start to get lower and lower during a climb, and it'll have the integrator. It'll have to it'll have to compensate by using the integrator in the control loop, and then when you level off, you may have too much throttle, and then you have an excess throttle, and then it's got to raise the nose to reduce the speed, and you end up wondering why the transitions between climb and level and descent and level don't look appropriate. So my recommendation is, if you're measuring battery voltage, do compensation, and just allow sufficient a bit of margin in terms of the TECS maximum throttle to allow for the drop off in battery voltage.
How practical would it be for us to compensate for that automatically?
Well, we currently have the capability to, the answer is yes, we could, but we'd have to know you have to make an assumption about the pack minimum voltage. And the problem is, if you have a lithium, polymer or pouch cell from manufacturer A, then it may have they may specify a minimum voltage, never go below 3.4 or 3.3 volts per cell. If you have a cylindrical cell from manufacturer B, they may be specifying it's safe to take that cell down to 2.8 volts. And that's a much bigger voltage range ratiometrically than the pouch cell.
And that's why in multi-rotors, for our thrust linearization, we do have a battery max, and then the battery can obviously go below, but that's safe range of gains that we can.
Yeah. Now with ArduPilot, so the comment was that with multi-rotors, we have that, what do you call it, the throttle ESC thrust compensation thrust curve, Here we have, these parameters are optional. So you can set up a battery monitor, but you're not required to set a maximum and a minimum voltage. It's a compromise between giving people so many steps they have to do that the whole process becomes completely intimidating versus something that will get them something working out of the box. Maximum climb. We have glide, and that's really what it says. You're trying to glide the aircraft down at the trim speed and measure the sink rate. My preferred method for doing this test is fly-by-wire A, and then I adjust the parameter called stab pitch down, and that's the parameter that lowers the nose when you reduce the throttle below the trim value or cruise value. And well, first of all, it's a good thing to do anyway, so that if you do have to fly on fly-by-wire A and you lower the throttle, that you don't have the aircraft trying to maintain a pitch angle, losing airspeed and stalling. And secondly, it's a nice way to do the flight test, because you progressively increase stab pitch down until the aircraft's gliding at the trim airspeed. And then the maximum descent, and there's no hard and fast rule other than don't overspeed the aircraft there. If you have a low drag airframe, you may end up with a result that's not operationally useful without resorting to air brakes. Now, this is a question. I don't use air brakes on the platforms I work on. Can anybody comment if we have air brake auto linked with throttle? We have that capability?
I have a branch that does it.
Okay, so for the recording, Tom Pettinger says he has a branch that does it.
We've got auto flaps, obviously, but it's not quite the same as the air brakes.
Yeah.
Yeah.
Okay.
What about negative brake, like negative throttle and stuff like that? Like for speed descent, do you include that into TECS as well, like somehow?
Okay, so the question is, what about negative throttle? I will talk about that, but yes, that maximum descent rate can also be, you can use the minimum throttle. It is usually set up for 0, but you can have a negative minimum throttle, and that enables you to achieve, significantly higher descent rates.
We use that to get where the throttle doesn't actually go in, but with the brakes detect less than. Just pipe that off to a brake actuator.
Yeah, so the comment is, can we use negative throttle to work air brakes? And I'd think that's, to me, I haven't looked at Tom Pettinger's branch. Tom's nodding for the record, and that seems to be the logical thing to do. Bye. think that's going to go on the item of things to do for TECS for this coming 12-month period. Okay, so we've done the maximum descent. Then we get into the tuning. Now, before I talk about tuning, I just thought I'd run a little test and show you how you can use guided mode as a good way to set up descents, climbs and descents for TECS. And the reason I like guided mode is because when you put the aircraft, you click on the map and you say fly to, and you give it an altitude, it'll circle that point. So you don't have to worry about the aircraft, positionally. But the other important attribute, you can set up a radius so that you end up with a nice shallow bank angle of about 15, 20 degrees. So you're not biasing the results with drag due to turn in the aircraft. And the other advantage is that when you set a height change in guided mode, the TECS gets a step change in height. So the height demand going into TECS will go from, say, 50 metres to 100 in a step, which means that TECS will try to climb at its maximum rate, or it will try to climb at its descend at its maximum rate. If you try to do that by putting waypoints and joining them up to do climbs and descents, by default, it will just try to follow the profile between the waypoints. So I thought I'd do show you an example of a settle test. Okay. So I'm using Mission. I'm using Mission Planner because that's what the vast majority of users would be working with, from my experience anyway. And when I've done presentations using Mav Proxy or Mav Explorer, I've had some blank looks, although probably not at this conference, but maybe for the broader audience. Okay, there we go. So okay, up there. 552. See that? Okay. By the way, who introduced takeoff mode? Because I'd like to thank them. Thank you, Tridge. So for those of us that can't be bothered planning missions, it's brilliant. Takeoff, arm, disarm. Don't worry about that. Yeah, I'm blaming Civil. Okay, I'm not going to wait for this to do its thing for too long, so I'm just going to take it to a fly here. 120 meters. And I'll set it up for a 200-meter radius. So while that's stabilizing, let's get a tuning page going. So there so unfortunately at the moment to monitor throttle, you have to monitor the servo output. I wasn't able to find on the nav link the actual throttle. VFR throttle is valid? Okay. Yeah. It's there somewhere.
It's not unbeatable. We need a search, control S search in here.
All right. Anyway, I'm going to put the monitor the climb rate. So take channel 3 out, get rid of that. We do have climb rate. Velocity is there. All right. So if you look for velocity Z in the, I'm just trying to find it. There's a VX. I think it's been blocked by the bottom of the bottom of the screen there. Anyway, it's VZ is the vertical velocity, is the vertical sink rate, not climb rate. So that's what you can monitor. And now it's ready to do a height change. So if we change altitude, we can go to, for example, 50 meters. And then you can monitor the achieved sink rate. You can monitor the pitch angle in the HUD to ensure that that's not exceeding the pitch angle maximum that you've set. And the other item which you can monitor is the throttle that's being achieved, which I'm going to have another look for under V.
It'll be under V. It'll be under. Might be under. Yeah, there's subcategory. I don't 3%.
Yeah.
I don't break this out. Yeah, that'll be good. And the bird radio out. Okay.
Up, no.
Give a little
Yeah,
search box in there.
Yeah.
Should be low.
Yeah, I can't get to it.
Oh,
Okay, all right. So I've been using the channel 3. There's a channel 3 out, which is the throttle. So using the screen, and I think the issue is maybe it's because I've got the bar showing. I'll try to go to part screen, and we'll do that again. No.
Yes, it's scrolled off the bottom.
Yeah, I won't spend too much time on it. So once you've got the aircraft in guided mode, I find this is a really good way to do text tuning for altitude. I've got it at 50 meters, and then I can say, for example, take it to 120 meters. And then you can monitor the climb, you can monitor the throttle usage, you can monitor the pitch angle, but because I'm not aware if there's a way to do multi-axis plots. So it really just, you just monitor one quantity at a time. And you can do some real-time tuning. So guided mode is recommended for this type of text tuning. It also enables you to do speed changes. For example, that's 22 meters per second. I can put 15 in, change speed. Yes.
what's the consequence of the assessment?
Okay, so the question is, what's the consequence of circling? The answer is it adds drag to the aircraft, but the drag is negligible. If your bank angle is less than 15 degrees, the normal G, normal acceleration induced by a turn at 15-degree bank angle is negligible in terms of its effect of drag and performance on the aircraft. And it depends on the aircraft. If it's a low aspect ratio wings are more sensitive to induced drag due to turning. A high aspect ratio wing, you could be at 30 degrees bank angle, and I don't think you would have a measurable effect on the throttle required. Something like a powered sailplane, for example. Yeah. So that's just an illustration of the tools available. Guided mode, nice big loiter. Step the speed up and down, monitor the speed response, step the height up and down, monitor the height response. And then you can start playing with some of the text gains. I'll leave that running and we'll talk about the tuning of the text control loops. So there's a global parameter on text which controls how aggressively text tracks, controls the speed and height error. And that's called the text time constant. And if you've calibrated the throttle and climb rate mapping correctly, that does correspond to the number of seconds required to remove the majority of a height or a speed error. Now, the default value is 5 seconds. That's very, very slow, but I'm not aware of any platform that's run into an instability at a time constant of 5. Assuming that the pitch loop is actually controllable for a human pilot operating fly-by-wire array. If once the pitch loop's been tuned correctly, a value of 3 seconds is usually quite safe. And the advantage with running the smaller value is that it essentially tracks height and speed more precisely. And if you get a change in speed or height due to a gust, it'll correct for that in a smaller amount of time. The integrator gain, the likelihood that you will need to change the integrator gain is I would regard as small. Now, the only examples I've seen where users have had to increase the integrator gain is if they have a platform that has significant changes in angle of attack or drag due to flaps, which we don't take account of for TECS. And you want the TECS to very rapidly retrim to account for the change in drag or pitch angle offset due to flaps. The problem with the integrator gain, if you start turning it up, you end up with a slow speed oscillation. And I'll show you what that looks like. So we can go to the configuration, and unfortunately it's not in our, we don't have it in our basic parameter set, but if I go to the parameter tree, we can jump straight to the TECS. Okay, so let's look for the integ gain, which is 0.3. Now, for example, what would happen if I set that to 1.0? It's out of range. Now, can you see how the vertical speed, it's now oscillating in vertical speed, and that's getting larger? Well, I think we'd better turn that back to the default gain very quickly. And this is where I help. I have a suggestion, and that is a panic button that undoes your last parameter change. Can we have that, Michael?
There it is. Dirt on the top.
Yep. Yeah. There you go. Ooh, now it's stabilizing again. So that's why I usually like to monitor sync rate on TECS, because if you have a problem with the tuning, it's going to show up on the sync rate before you start seeing it on airspeed. You'll see it on pitch angle. Pitch angle can be much more a function of gust response. So yeah, look at height rate. And if you start seeing that type of behavior, well, yeah, revert your gain very quickly or switch to FBWA. Okay, now pitch demand tuning. The pitch demand controls the exchange of energy between potential and kinetic, and there's very little that you really need to do with the pitch loop except potentially adjust the damping parameter. Now, the damping parameter means it reacts to the rate of change of airspeed and the rate of change of height, right? So it tries to anticipate the build-up of the error. The problem is, as you can imagine, airspeed is a noisy quantity. It's a noisy measurement. And now we're trying to respond to the rate of change of a noisy measurement. And the rate of change of a noisy measurement is noisy. So if you start to increase the damping on TECS, what will happen is you'll see the pitch angle, it will start to become very active on pitch. So it'll be demanding lots of small pitch angle changes, 2 degrees down, 2 degrees up, 3 degrees down, 1 degree up, trying to control the noise on the airspeed, reacting to noise and gusts that's encountered. And you really don't want the controller doing that. But there are some situations where you end up with some slow speed limit cycling on the, or slow speed oscillation on the height, where sometimes a bit of extra pitch damping is a good thing to have, but I wouldn't increase it in increments of more than 0.1 at a time. Then we have the speed weight parameter. The speed weight parameter, once again, don't touch this unless you have a specific reason to do so. The weight parameter is just another way of controlling the compromise between speed and height. So if the aircraft is low on height and it's low on speed, obviously you want to add throttle. But what do you do with the pitch angle? If you climb, you're going to get your height back faster, but you won't get your speed back as quickly. If you don't climb as much, your speed's going to come back up, but your height's going to stay low. And the weight controls the compromise between speed and height control. It's a strange parameter in the sense that if you set it there, the clue is in the word speed. So 1 is balanced, and that's default. A value of 2 means that the pitch completely ignores the height and only controls the airspeed for pitch. And for up and away flying at altitude, that should be a pretty good setting to use, because it means the aircraft isn't constantly responding to gusts in terms of its elevator response, and it's flying closer to the optimum angle, the optimum airspeed, and it can lead to higher efficiencies. And it's the only setting you can use for gliders, because they can't control their speed with throttle. They have to control it using pitch angle. On the other hand, if you've got something with a powerful engine, very fast throttle, and you want accurate height control, you could set it to a value of 0, where the pitch angle completely ignores the speed, and all it tries to do is control the height, and then the throttle has to do all the work with speed control. What you use, that's up to you and your application. And then the throttle demand tuning is really only one tuning parameter there. Once again, there's a throttle damping parameter. I can think of about maybe 3 occasions in the last 5 years where I've known of an application that's actually required the throttle damping, that's required adjustments. Same rules apply, go in increments of 0.1, and it's just there for slow speed, very slow speed oscillations in throttle. So if, for example, we were to run our simulation model and go to here, and we were to demand a speed change, so that's sitting there. I'm going to take that down to 15. Sorry, at 15. So let's say I was over to 18 meters per second. There you go. And it's responded with a bit of pitch angle with the climb rate. It's dropped the nose slightly to pick up the speed because it's trying to control both. And now it's converged again, and now the speed's reached the value it's required. So you wouldn't make a change to tuning on the basis of that. But it's there if required. But it does make the throttle noisier and more responsive to gusts, because the throttle is now responding to the rate of change of speed. Speed is noisy, and rate of change of height. And then we get to the landing approach. I've broken the parameters out in the slides. You'll have to look at them for your own reference later. Feel free to come and approach me and ask questions about it. But we have parameters which specifically modify the landing approach behaviour. We have a separate time constant, so we can run a smaller time constant and a much more aggressive height keeping during the landing approach. We can, if you're using reverse thrust, you need to allow a higher sink rate other than the default TECS sink rate during the landing approach. For example, reverse thrust setups would need to set the approach S max parameter, and then you may require adjustments to the damping for something that responds faster to gusts. The remaining, yes.
When you transition to the landing on the lower change,
yes.
how do you phase between, like, is it a step change or is it like actually the explanation between them.
Okay. Some of the parameters basically will step, like your sync rates, and the airspeed, for example, which are these parameters here. But there's one here which is the speed weight parameter. You know, I talked about speed weight, how if it's set to 2, it's using pitch for airspeed, and if it's 0, it's pitch solely for height. Well, this parameter, the default value is -1, and what -1 means is that at the start of your landing approach, you're using the speed weight that you were using previously. By the time you get towards your flare position, it's actually dropped the value to 0. So that by the time you enter your flare, it should be controlling the height and completely ignoring the airspeed using the pitch. So yeah, that speed weight phases, basically blends. But the other values unfortunately do switch. So you may observe some discontinuity in throttle and elevator response on entry into approach, but usually that's associated with pushing over onto a glide slope anyway. Now, if you're not landing with an airspeed sensor, there's an option there to adjust the sort of trim, the throttle value for level flight that's used in the lookup. So remember, we had this curve. If you don't use an airspeed sensor that relates pitch angle to the throttle, or during the landing, you can go to use the TECS land throttle as that sort of trim point, and that's just so you can make adjustments to your approach speed if you're not using an airspeed sensor. Okay, and then the flare maneuver. Now that's been rewritten since the last conference, and we now actively control the flare height as a flare demanded sync rate as a function of height, and only the first 2 parameters are, for 99% of cases, are what users will have to adjust. I've given some notes there. You can look at the parameter descriptions, but these are the important ones. And the reason is, if you have a look at that diagram, that's what's going on with the parameters. So we have the height at the start of the flare, and that's height above ground. It's either an estimate, or as it actually comes from the measurement using the LiDAR, or it's an estimate that's updated using the LiDAR, I should say. And then we have the flare height, which is the height that TECS tries to hold off the flare at. And then you can see here that we start off with the sync rate that we enter the flare with, and then when the aircraft has descended down to that flare height, which is I think we're at 1 meter by default on flare height. Yeah, 1 meter. And then the demanded sync rate after that will be at TECS land sync, and our default is 0.25 meters per second. And if you're measuring height using a LiDAR, that most platforms will do a nice flare hold off maneuver and a reasonable touchdown. And in fact, if you saw the Yak landing at CMAX or day before yesterday in the aerobatics display, not the yellow Yak, the one with the red striping, which was landed in the automatic mode, that was using the default landing parameters. There you go. So that's what it looks like. These other parameters just control this. These are the same parameters, but just for the flare maneuver. So you can change the time constant. You can have a much more. The land time constant also affects the flare, and you can have a more aggressive height control in the flare. You can have more damping to respond to gusts. You might want to limit the maximum nose up pitch angle so that you don't allow the aircraft to pitch up excessively during the flare maneuver. Just as a safety, it's really just to handle unforeseen, changes in conditions. I would normally set that. I mean, what's the default? 2 degrees, I think, is the default for that parameter. I know some people would would use 5 degrees for the maximum pitch up angle for the flare, and then you can set the damping separately. The final parameter is land flare aim. Now, this is a slightly strange parameter in the sense that the landing code tries to estimate how much time the aircraft will spend flaring. and it takes the speed along the ground and says you're going to take this much time flaring, therefore you're going to cover this much distance flaring, compares it to the distance from the flare start to the flare aim point and says, well, that means the flare is going to require an extra 20 metres or 30 metres. Therefore, you should probably move your aim point back to allow for the fact that you're going to overshoot the landing point while you're flaring. So this flare aim is a strange parameter in the sense that it sets how much of that calculated flare distance do you want to compensate for. So if you're overshooting your aim point consistently, you make land flare aim a bigger number. And if you're undershooting, you make it a smaller number. Look at the parameter description. It's probably not something most people have even bothered tuning before. But if you can get it, yes.
Quick question regarding that flare aim. Right in the older code,
Yep.
it was very dependent on headwind.
Yes.
Does that still suffer from this?
Yeah. Okay. So the question is, the old code, it was quite dependent on headwind. What about the new code? New code, less dependent on headwind because of the flare height sink rate is much more deterministic with height. So you get better results. But we also have in the new code another parameter, which I haven't touched, which enables you to ensure a minimum, essentially adds additional airspeed as a function of headwind to allow for the fact that as you flare through the wind gradient, as you come down, you might have 10 knots of wind at 3 metres. When you get down to half a metre for the finish off your flare manoeuvre, you don't have 10 knots of wind. You've effectively lost 10 knots of airspeed. So anyway, there's a parameter which enables that to be compensated for. I think we did that by default in the code. I can't remember the name of the parameter off the top of my head. Somebody here will know.
Sorry. Yes, I think we do.
Yeah. Anyway, that's so the combination of the new TECS deterministic, more deterministic flare manoeuvre and the parameter that adds additional airspeed. Land wind comp, there you go. So the new TECS and land wind comp, put that together.
For 50% of the wind estimate.
Yeah. So that gives us certainly more consistency with our touchdowns. Okay. Well, we're out of time now. So.
All right. Okay. Well, any final questions before we? Okay. So thank you very much, Paul.
Thank you.